Here we have question 4 from homework 12. We're going to solve this differential equation using the Cauchy-Euler method. So when x is greater than 0, we're going to let x equal e to the t. D will represent the derivative with respect to x. Script d will represent derivative with respect to t. And this pre-superscript ty will represent a function y of t, just to save time in writing out. So these being the conditions, x times d will be script d, x squared d squared will be script d times script d minus 1. Next step, we're going to put the differential equation into its operator form after making the substitution. So we have 2 times d minus 1 is d squared minus d squared minus 3d squared minus 3d minus 3. Operated on ty is 0. And we're not concerned about the homogeneous or non-homogeneous part, since the equation is homogeneous to begin with. So grouping like terms, we get this operator function, this operator form of the equation. We're going to call it f of d for convenience. So given that this is f of d, we can write the characteristic equation for the same thing, factoring out this polynomial gives us these factors, so we'd see that m equals -1/2 or 3. That tells us that the fundamental solution set, oh, we didn't write out that step. Well, what that tells us is the fundamental solution set is e to the -1/2 t plus comma e to the 3t, and that ty is the all linear combinations of those two elements. So this is the solution in terms of t, and remember that x equals e to the t, so t equals log x. So to convert this into terms of x, we replace t with log x, which gives us y equals c1 x to the -1/2 plus c2 x to the 3rd. Now to solve for when x is less than 0, we make the substitution that x tilde is -x. Alright, going back and, by the way, this is me coming back from a break. When x is less than 0, x tilde equals -x is the substitution we'll be making. So d will represent now dy dx tilde, which by the chain rule is negative dy dx. And we'll again make a substitution similar to what we did before, but this time using x tilde, which we could not do unless we did make the substitution x tilde equals -x, since e to the t is always positive. So we'll first rewrite the differential equation using x tilde. So 2 times x tilde squared times y double prime. This is positive when we substitute x tilde in, because -x squared is positive, and then the second derivative dy dx, rather the second derivative of y with respect to x tilde is also positive. So this is a positive term minus 3 times -x tilde, since it should be clear why, and -y prime minus 3y equals 0, and this is where x tilde is greater than 0. So we'll use the transformation x tilde equals e to the t, and we'll then write it in operator form. So it will look just like it did when we solved it up here, because simplified, this is 2x tilde squared y double prime plus no, minus 3x tilde y prime minus 3y equals 0. Which is just like the form we have up here, but replacing x with x tilde, since this is exactly the same as this, most things considered, disclaimer, the solution y in terms of x tilde will look like so, just as it did up here for x. So transforming this into terms of x, we'll just replace x with negative x tilde with negative x, and we have found the solution for when x is less than 0, because we solved for this when x tilde was greater than 0.